Bonjour. Aujourd'hui, nous avons Fabian Gloeckle qui fait son doctorat à l'École des ponts et aussi dans une équipe Meta AI. Il va nous parler de l'utilisation de l'intelligence artificielle pour trouver les preuves des théorèmes, des choses comme ça, en anglais.
Merci pour l'introduction et je suis très content que vous soyez tous toutes venus ici. Et j'espère que ça ne vous dérange pas si je fais mon discours en anglais. So I'm Fabian Gloeckle. I'm doing my PhD in Paris with Amaury Ayat at École de France and with Gabriel Senef at Meta AI's lab in Paris. And today I want to talk about two technologies that I think can change mathematics profoundly in the years to come. And the first of these is formal mathematics. So formal mathematics means programming languages whose syntactic validity check performs a semantic proof correctness check. So in other words, you're going to write your proof in the system, and when the compiler reads it and returns no errors, you can be certain that this proof is correct. And this works because proof search certainly is an art, but proof verification is purely mechanical. If you know P implies Q, you know P, then you can just put Q on top of your state of known facts. And so this system of verifying mathematics programmatically has been implemented in a bunch of software systems. The most famous of these are Lean, Isabelle, and the French one, Coq, now Rock. And what I'm going to say about each of these, I'm mainly working with Lean, but what I'm going to say will apply to each of these almost exactly the same. And so why formal mathematics? So there's this grand vision of turning all of mathematics into a formal system, fully verified, fully queryable, and fully interoperable with other parts of mathematics. And so to spell out this grand vision more clearly, I think there's several advantages of doing mathematics in a purely formal way, or at least of turning mathematics also into a purely formal artifact. So the first advantage clearly is certified correctness. And mathematicians rightly are somewhat paranoid about the correctness of their proofs because they know that if a single piece somewhere down the huge building of mathematics breaks, then everything can break. And so there's many quotes by famous mathematicians. So here I have Vladimir Voevodsky, who was telling the story of a grave mistake in one of his proofs, where he said, no one of the readers noticed the mistake. A technical argument by a trusted author, which is hard to check and looks similar to arguments known to be correct, is hardly ever checked in detail. And so this is the worry about the mathematical reviewing process, that it doesn't fully find all problems with mathematical proofs. And even though mathematics as a whole turns out for some magic reason to be quite robust to such human flaws, it is still concerning that so many even high-profile papers can have mistakes. So certified correctness is certainly one of the big advantages of formal mathematics. But what's more, a large formal mathematical library could also bring us closer to this vision of Bourbaki, of a unified library of mathematical knowledge, where you do not have to worry about slight inconsistencies between certain definitions, about the question of who takes what as a definition versus what as a theorem. And you can use any theorem from anyone with absolute knowledge that you're applying it in the correct way without any hidden assumptions that you may have overlooked. Thirdly, formal mathematics allows the deep integration of computer algebra system. And deep integration here means not just copying something from Maxima to LaTeX and then back, but the knowledge that whatever the output of the computer algebra system is, was certified and verified in this formal system to make sure that it's actually applicable in the situation you're using it for. But then you can also, once you have this mathematical library of knowledge, you can also apply integration of, you can integrate modern automation tools. So even classical ones like library search, for instance. So in this Lean system, it is already commonplace that authors write And this reduces the statement to something that I know to be true from the library, but I'm not going to tell you which one you're going to find out. And then the system finds it and can put the name in this place. So this is already a huge improvement to the workflow of mathematics compared to going to a library and looking for the statement that you need to hold. And lastly, it turns mathematics, which was like a very lone exercise in some sense, into a true dialogue. So usually, when you do mathematical proving, you are both the environment and the agent. You're the one who suggests a step and who has to execute the step. But now that we have the systems, it turns mathematics into something really interactive. So in Lean, for instance, in every line of your proof, you will have associated a proof state. And this tells exactly what you know and what you need to prove at this point. And if you move your cursor one line down, you see that the proof state changes. And it is not your job to predict how the proof state changes. It is the job of the system, and you're talking and playing in that system. And so this is something that makes mathematics very fun and actually also very addictive. And there's many mathematicians that fall into this trap and become addicted to formal mathematics and build their entire careers upon it. So the second big technological breakthrough of the last years is language models and artificial intelligence. And so these are the systems that you know already to be good at undergraduate math. But then there's even the Terence Towers of this world who say, it proved to be useful in giving me ideas, in doing research, in writing code, in checking calculations. So already it is slowly transforming, these systems are slowly transforming how mathematical work looks like. And I think we can be quite confident that it will be even more so in the years to come. But what's more, language models are also extremely good at writing code. And now I've told you that formal languages are code. And so many people have had the same idea, which is coupling those formal proving languages with language models to provide code that can be checked and that gives us certified and trustable outputs of language models that we can use in our math without having to be afraid of hallucinations and mistakes of the model. So a very quick introduction into what language modeling works like. So language models are trained by teacher-forced next word prediction. And so this just means that at every position in the text, the model has to predict the next word. And whether it's correct or wrong, it will just be given the ground truth next word, and then the prediction continues from there. And so the targets are simply the shifted inputs, and then the prediction has to match those. And so the remarkable fact is that this is a super simple training regime, and yet it leads to all these amazing models that we now see out in the wild. And two statements are true. The first statement is these are just stochastic parrots, and the second is there's true reasoning happening under the hood. So true reasoning, for instance, when you have to predict how the proof would proceed, and you have to think about which would be the most logical continuation of a given text. And then when you use these language models, you use them autoregressively, meaning you copy the outputs back into the input, and so you add word after word, and the model continues from there. Okay, so with this brief introduction into those two techniques of formal methods on one hand and language modeling on the other, I want to dive right into this question of how can we couple those technologies best? What are the different mechanisms, the different ideas for how to couple them? And there's been many works in this area, and it's somewhat messy because everyone is doing their own system, and it's hard to compare systems with each other. I will try my best here to give you a sense of how different methods not just work at one point, but how they scale, and we will try to collect all the evidence that we have right now. And I've deliberately tried to keep that a bit short because it can be quite technical, but if you're interested in more of this, I would advise you, I gave a version of this talk at EHS last summer, where we went into these parts in way more detail. Okay, so the different methods for coupling formal systems with language models. So the vanilla version is just writing down the whole proof as one big file text. And then there's various extensions of that. So you can turn that into a multi-turn interaction with the environment where you read in the feedback. You can add so-called reasoning models on top. You can hierarchically decompose a proof. And conversely, there's tree search methods, which operate on a lower granularity, and the basic version is best first search, and then there's extensions of that do more computations, which are called Monte Carlo tree search. And for each of them, I will briefly jump into what they are. We won't spend too much time on them, but just to give you an idea of what the different options are here. So I've also tried to put this zoo of ways of interacting with such systems like Lean into this little cube. So to stress the point that these can be different directions of extending the standard approach. So the standard approach, I would say, is this direct whole proof generation. And then you can extend that by saying, okay, I will spend more time by reasoning in natural language up front. Or you can say, I add an execution, and then I get a system that reasons more in the sense of interacting more with the environment. Or you can go into a line level, tactic level, very granular model, and then you can add more reasoning by doing test time reinforcement learning with Monte Carlo tree search. So this just to stress that these are different directions of extension, and sometimes they can be compatible, and sometimes they cannot be. So let's analyze a bit the direct full proof attempt. So I would like to understand how the scaling behavior of these methods works. And so when I mean scaling behavior, what I can do is I can generate lots of texts and evaluate each of them, and then I can check the probability that at least one of them is correct. And this is called the pass at k metric. So I generate k texts and I check that at least one of them is correct. And note the logarithmic scale here. So these models have a certain scaling behavior, but it's quite bad because it's always logarithmic in the sample budget. And so this is from a coding model, but the same applies also to whole proof generation models. And if we want to understand why this logarithmic scaling makes sense, we can assume, for instance, that there's n fundamental actions in every proof, or in a certain proof. And then if P is the success probability per action, then we have an exponentially decreasing probability of success of P to the n. And so you can say 1 over that is the amount of samples that you roughly need in order to find at least one good one. And so this is the expected k in some sense of this pass at k. And now if you follow Timothy's courses, you should to take the minus log of that and call it an entropy. And so this is an information quantity of how much information is needed for a model to understand in order to do a certain proof. And so people were doing these sorts of graphs a bit more diligently, and they found a scaling behavior of the form the exponential of a power law. And I just briefly wanted to mention that if you do a change of variables in which you go out to this entropy, this information quantity, then you figure out a nice distribution that is assumed by this modeling. And this distribution is that this information quantity contained in a certain example is a Gumbel distribution, and you can try to make sense of that as a term, as an extreme value distribution. So just to understand, these people matched extremely closely certain scaling graphs with their model, and we think we can give a mathematical meaning to why that might make sense. So this is the scaling behavior of direct single attempt proving. Now, the other basic technique is called best first search, and this is a technique that operates on a line level. And operating on a line level doesn't help at all if you don't execute the code. In fact, if you don't execute the code, then it will be strictly equivalent, if you don't execute it in between. Because if you don't execute it in between, then the method will be equivalent to whole proof generation that we just discussed. But if you do add in execution, then you actually do this interactive theorem proving that I mentioned at the beginning with the states that will be interpreted by the model. And so these states can be really complicated. So this is out of an actual proof by Patrick Masseau. And you see all these assumptions here and the thing that you need to prove. And if you didn't add in the states for the tree search model, then it could be pretty hard to figure out what exactly Lean is calculating internally here and to predict that in order to write such a long proof. And so best first search, you can see it as an enumeration of state action sequences by the cumulative probability. And if you want to be efficient, then you cache states that you've already seen, and that turns it into a tree search data structure. And so what I mean by the state-action distribution is this whole sequence of states and actions. And then I can decompose that step by step. And the environment is deterministic, so I can cancel, like I can remove these terms. And what I get is the probabilities of the action model only. And this is exactly what people use when they use their best first search, when they use the model probability to direct the best first search. So the way that looks in practice is you first do a supervised fine-tuning on proof states from some data set. So you have the state before and then the action, and you can also train on the state after. And your task is, and after fine-tuning, you will use that model as is. So it will be fixed at test time, and this is what gives you your performance. And so when we did the study on these systems, we found like new methods of doing more efficient fine-tuning of language models on small data sets, and a better way of like predicting which language model, which fine-tune would behave optimally. But ultimately, this method is not adaptive enough to scale very well. And so the extension of this method that does more like test time reasoning is called Monte Carlo tree search. And this is the method that was used in AlphaGo, AlphaZero, or also AlphaProof recently by DeepMind. And so the method here is that at every position, you will expand the tree of options, like what you can play or what you can do. And you turn these computations that you perform, like the evaluations of later states that you see, you turn these into intuition by training your intuitive evaluation model on the outcomes of these three computations. So this was a pretty abstract description of what is going on here, but the important thing is, like you do like a chess player, you calculate the tree in advance, you evaluate the leaves of the tree, and that gives you like your best guess of what you should do at the root of the tree. And when you apply this to theorem proving, there's one little extra complication that you have to deal with, and that is that applying a reasoning step can lead to multiple sub-goals. So you can apply induction, for instance, and then you will get an induction base and an induction step that you need to prove. And this turns the data structure of a tree into a so-called and/or like minimax tree. That is the correct data structure for doing this sort of theorem proving. But the important thing about Monte Carlo tree search is that you can use it as a test time training method. So previously, people thought of reinforcement learning as a training time method. You have your large data sets, you train on it, and then when you evaluate, you have typically a small evaluation budget, and then you see how well your model performs, and then you put that into your paper, and that's it. But actually, what people care about when they want to use a model in the real world is how, like, just getting the maximum performance on the test set. So if you have challenging theorems that you want humanity to solve, then you're fine with adapting to the test set. And you don't, like, this is not cheating, but it's actually important to adapt to your test set. And so reinforcement learning as a test time method means that when you receive your test samples, you're still allowed to change your weights and to adapt to these testing time samples. You're not seeing the proofs there, but you're still adapting your policy to the specific data sets in question. And so the cool thing about this is that if you do this, then your data is perfectly in domain by definition, and this is exactly what language models in machine learning more generally like to have. And so when we did this methods, we got a very efficient proving model from very small data sets and with very small amounts of compute. So you see typically competitor models used in the orders of millions of different training statements in order to exercise their proof search on during training time. We only did training on the test set, and we compare faithfully to the baselines, because both the baseline and our method compare cumulative solve rates over the course of the entire training. So both the baseline here and our method does test time training in that sense. And you see that with many of these papers don't even dare to mention the amount of compute they needed because it was huge. Ours was quite low for machine learning standards and reached almost the exact same performance levels. And this, of course, comes at a cost that if you're very good at test time training, you do pay a price here in terms of generalization to other data sets. So if you If you evaluate on a fixed data set that's unseen and not adapted to, then you get worse numbers than if you do this adaptation strategy. Yeah, and this has been used in practice by DeepMind. It was called Alpha Proof. Last year, it won a silver medal in the IMO. We don't know how much compute they used. It must have been quite a lot, but they managed to prove, I think, 4 out of 6 problems. And if you look at the proofs, it's really funny because this is alien mathematics in some sense that we, as humans, if we look at those proofs, we cannot fully judge what's going on, unlike in other lean proofs that are more readable. But this system has been training for such a long time on its own outputs that it diverged a bit into its own style. You also see that there's a drawback here, which is there's a lack of global workspace or planning. For instance, here the authors put a comment saying the model proves a lemma that it doesn't need, but it's still 16 lines, and it wasn't aware that it wouldn't need it because there was no global planning going on. Everything is somewhere in a proof tree search somewhere. And if the tree search concludes, then it concludes. Okay, so coming to the extensions of whole proof generation, and I want to come to reasoning models first. So reasoning models, the idea is to prepend some text that will be generated by the model before you produce the final answer, and you can use that text that you generate before for thinking or reasoning. So you can do computations, you can play with different hypotheses, you can backtrack, you can search, you can question your own behaviors. So this is an unsupervised part of the whole trajectory that the model is free to use for its own sake. And what OpenAI and then DeepSeek and other model labs found is that if you do reinforcement learning on verifiable math questions and you do not constrain the length of the outputs, then automatically the models will start to produce longer texts. And in these longer texts, they will start doing these sorts of higher order cognitive behaviors like backtracking. And so what you want to observe, and what you did observe here in DeepSeek's model, for instance, was that over the course of training, the average response length goes up, and with it, the evaluation scores also go up. And so the same method has been applied to lean, and it was called Kimina Prover by Project Numina and the Kimi team. And here also you see, so the response length goes up over the course of training, and with it, the evaluation scores. And the model here really, it has one single attempt at producing an answer. So the final code that it submits is the code that will be evaluated. But before, it can freely think about what it wants to do, unlike other models that were directly trained before to produce this code without any thinking before. And so you can see that it really looks like we would think it would. So it uses natural language to reason about the problem. And when it reasons, it's not just beginning to end thought process, but it's really trying out different strategies and questioning itself and really looking for the best way of doing something. And then when you read the proofs, they're slightly odd, and that is due to the fact that the model only has this one single attempt at producing the final proof. So it's very conservative, and it doesn't like doing any steps that could be dangerous, and so that's why they become very verbose and long in the end. Yeah, and so the model works really well, but it's hard to judge again how well it works, because first it's a 10 times larger model than the models they're comparing to. It also produces 10 times longer answers, so in some sense it's expected, and we should compare for the fact that correct for the fact that it uses 10 times more compute. But also it uses way better data sets that were annotated by hand and had significant volume. And so ultimately it's hard to judge whether after doing all a fair comparison, whether the method would be here or whether it would still be above. So the nice thing about the Kimina model was that it studied exactly one thing, but often in this domain it's hard to compare different models because we don't have very good baselines. Yeah, ultimately the question is reasoning itself may not be enough, because as I mentioned, if you don't execute your code in between, then you could become very anxious about making mistakes, and that's what we saw in those examples here. Okay, so this is reasoning. Now, if I say we should allow more interactions with the environment, this is the exact idea of multi-turn agents. So as computer scientists, we love and hate bugs and error messages. It's what we spend most of our time with. It's annoying. At the same time, error messages are supposed to be very useful and to help us understand what is going on, and developers of programming languages spend lots of time developing good error messages that are informative. And so here, for instance, you can see that like when Lean complains, it says, I didn't find an instance of this pattern in the target. And then we can observe, oh, it's true, there's no nut.suck in this goal statement. And so we can understand what is going on, and we can try to repair our proof based on this feedback that we receive. So error messages are supposed to be useful. And if they're useful, then we should like use them and try to fix our code. And so this has been extensively studied in Python, but also like now things are popping up in Lean, and we have initial studies on Lean as well. And so in Python, we have a very nice and clear paper from our team at Meta. So here what you see is a single turn interaction model compared to like models that have more attempts at producing an answer. And still it's compared on a fair comparison, meaning that if you have 10 times more attempts, then you have 10 times fewer overall attempts. So like if you have 10 times more interactions, you have fewer overall attempts. And so we have, so here there's the numbers on the untrained instruct model, and then there's the numbers on if you do reinforcement learning on top. And what you can see is that the instruct model has a very nice scaling behavior in terms of like pass at k by budget. But somehow, if you do reinforcement learning with single turn interactions, this scaling behavior becomes damaged. So the models are still better initially, but then they taper off and they can't really scale as well as the other methods. Not as well as the original model untrained, nor as the reinforcement learned models if you use multi-turn interactions. And so that for us is a clear signal that like multi-turn interactions adds the amount of reasoning and understanding that the model needs in order to continue improving its behaviors if it's given more compute. So if you want to think about it a bit maybe more theoretically or heuristically about why multi-turn interaction might be a good idea, like one very optimistic or idealistic answer that I can give is, let's make a very strong assumption, namely, there's n independent decisions to make here, each again with a success probability of p. And so as explained before, like we have p to the n success rate for the standards whole proof generation. But if we make the very strong assumption that fixing errors always works, then we can calculate the estimated amount of errors in a piece of code, n times 1 minus p. And this will be like, if we always manage to fix one error and move to the next, then this will be the expected amount of turns needed to bring one such piece of code to success. So clearly this is a very optimistic assumption to make, but what it shows us is that it turns exponential scaling into linear scaling, which would be obviously a very great achievement. So if we evaluate such models, the way I like to look at them, so this was us evaluating proof sketch generation. The way I like to look at that is the number of overall fresh new attempts and the number of turns per attempt. And then like the hyperboles here are the ISO compute curves where the same amount of language model calls have been used. So number of attempts times number of turns equals constant. And then if you follow one of these lines, for instance, and look at the pass rate, we see that at very high numbers of attempts but very low numbers of turns, the pass rate doesn't start very good, like in the blue zone, and then can move all the way up to like this pinkish colors. Yeah, and also like qualitatively looking at such models is very nice because it really feels like someone is working with you on your GitHub and committing code that can improve the text. And it's very like, it can be very localized and sensible suggestions that can come out of these sorts of models. So we have to be, so Gödel Prover v2 was one of the first models that did that at scale. However, like we don't know exactly, no one evaluated under a fair comparison, as I mentioned, like this. So we don't know exactly, like the pass at 32 here compares to 3 times the amount of compute of the baseline. So it's unclear by how much the methods helps in this case, if at all. But it's still interesting to have a very strong model that has bug fixing ability baked in. So now, lastly, there's a method called hierarchical sketching or hierarchical decomposition. And so this should feel quite natural to mathematicians, which is when you meet a statement, you can first try to decompose it into a bunch of steps that you would have to prove independently, or lemmas, and then you can work on all of these lemmas independently. And in math, it's lemmas, and in coding, we also have this behavior with decomposing into functions. And so the reason why this should work is, let's say the reward here means whether a lemma proof was successful, or part of the whole proof was successful. And on the rows, I put the different attempts on the ith lemma. And in the columns, you can see that as a proof for the first lemma, a proof for the second lemma, a proof for the third, and so on. So this will be one independent whole proof attempt in one column. And now you can see that it should be better to first take the maximum among those and put all of these maxima into one column, then to look at each column individually, and then try to find one of the columns that's overall succeeded. So if you maximize the pieces and then sum, then it's better than to first sum and then try to maximize those sums. And so, yeah, like if on each lemma you get direct feedback, and you should use that direct feedback and not just plug everything together and evaluate the whole thing. And so if you want to see such systems in action, there can be small human-written solutions, for instance, that don't make up a complete lean solution, but you can very easily translate those human proof steps into corresponding lean lemma statements or have statements, and then it will be the task of some automatic prover to fill in those gaps. And if you couple two such systems, then you get a very nice and powerful proving behavior. So most works that I know of that work with this like lemma decomposition, they take fixed models and then they evaluate those fixed models on this mechanism of decomposing a proof into lemmas and proving those lemmas. But the real question is, can we train a system that decomposes into lemmas and proves those lemmas? And can we get a reinforcement learning that beats the other ways of doing reinforcement learning with lean and language models by baking this behavior very deeply into the model? And so these are like our first like initial signs of life or success for this method. So you can see here the cumulative pass rate over the training set. And you can see that the sketching behavior, initially, it proves way fewer theorems because it's also a more heavy inference technique. But later on, it proves worthwhile because overall it solves more problems of the training data set than the other methods. On the evaluation data sets, it's still less clear. So it plateaus late and sometimes not as high as the other methods that typically plateau very early. What's also interesting is that entropy of like the diversity of a policy is very important in reinforcement learning, and what you see here, that it maintains a slightly higher entropy than many of the other methods. So these are the first signs of success that you can do something like training specifically for such a structured hierarchical inference task. So people typically, they take a fixed model and then they start playing with it and do decomposition into lemmas and proving those lemmas. And this gives very good numbers if you download the strongest models from the web. But if we know that we can train for it, then later generations of models could be even stronger because the next generation of models that people will download will already have these sorts of behaviors baked in, and this is what we are working on. So what I like about this is that it moves away from like this idea of reinforcement learning as fixed data sets fed to a prover and sent to a trainer, and moves toward what you could call dynamic reinforcement learning, where the distribution of the training data itself is changing over the course of the training. And it is changing because this lemma decomposer will produce different lemmas over the course of the training. And so this will still receive a finite fixed data set, but in the end, what the prover will see changes over the course of training. And this is the same for lemma decomposers or conjecturing methods, where there's a model that conjectures a lemma, because those are very related in this sense. So now I would like to take one step back and like situate all of this, what I told you about, different methods, scaling behaviors, this paper did that, this paper did that, this paper did that, and try to like put it a bit in a more like global understanding of what learning might look like in the years to come with language models. So at a very high view, like we can distinguish different like types of learning, and we can compare biology with machine learning. So in biology, we have like the evolutionary process that generates the DNA. Then we have learning in the sense of like synaptic weights and connections changing. And then we have something that is like fast adaptation, where people put things into their working memory and will learn a new word in a new language by just being told, or episodic memory, where you remember how you did the same thing yesterday. In machine learning, the correspondence of DNA, you could say, is like the research that the community is doing and the algorithms that we come up with. The learning corresponds to like training behaviors, like when we come up with weights of language models, and these weights correspond to the synapses. And then the interesting thing happens at the adaptation. So here, like this is called in language modeling in context learning or reasoning, and this is what happens at the activation level or in the tokens that the models produce. And so, as I said, this is where like the cool things are happening now, that models are increasingly strong. And this is what we need to get right in order to get the best performance in terms of real-time reasoning. And so to go back a bit like in history of like how language models evolved and how we're using them. So initially, there was only pre-training, so next token prediction, weakly supervised. And if you wanted to use it, what you got was a text completion engine. So you can give it a prefix and it completes that into a full text. There was one trick that you could use to turn it into something like a question answer, which is few-shot prompting. You put question, answer, question, and then you hope that the model picks up on a pattern and that the most likely continuation of the text is the next answer. And so this was a way to get something interesting out of pre-trained language models, although they were just a completion engine. And people said, okay, fine, actually this is a bit annoying of having to do this few-shot prompting. It's not super stable, like it depends a lot on the examples. So people invented fine-tuning, which meant putting exactly those types of data that we want to see more often in the behavior of the model into a second training stage. And so in this second training stage, like the content will be question-answer pairs, or will be multi-turn conversations. What I say, what the model says, what I say, what the model says. So these are the multi-turn dialogues that made the chatbots that we all know. Now, on top of these chatbots, people again said, okay, let me do something cool. Let me couple up the chatbot with an environment, tell it what the environment produced, which states it produced. Or like when it thinks a bit, like I will just tell it to think a bit more and to reflect on itself, and then it will think more. And I will tell it to think more and to think more until I like the final answer. So the techniques were environment interactions and self-reflection prompting. And again, people said, okay, that might be a bit annoying that it's not super stable and we need to prompt it. And so like the next revolution was reasoning models or agentic models, trained via like these new methods of reinforcement learning from verifiable rewards. And so we put those environment interactions and those reasoning traces where the model reasoned for a lot of time before providing a very short answer into the training system. And here you see there's a reward being observed at the very end because it's reinforcement learning. And so this is the type of models we're currently with. And people are building amazing things from these models. People are moving way beyond simple, okay, I send something and then I get something back. And they're moving toward like flow charts of like different algorithms that just use a language model as one node in this flow chart. So for instance, in natural language mathematical reasoning, there was a paper on solving IMO problems from the International Maths Olympiad with strong like reasoning models. And here the idea was just to put them into a small loop that says, after you provide an answer, try to improve it even, then you send it to a judge or reviewer or referee that will try to tell you how to improve it and whether there's still mistakes and problems in that. And then we will revise this text until it matches all quality constraints, and we will submit it. So this is a very simple loop, and yet it proved very powerful in getting a model with 40% accuracy to a model with 80% accuracy, which is important if you want to use it on actual problems. Now you can use similar systems for lean, for instance. So you could call these heterogeneous systems, or you could call them multi-agent, because there's multiple prompts with different behaviors. So here, for instance, you have decomposition into lemmas again, and you also have like this bug fixing until something is good. And like these systems, like nowadays systems use many of these components that I mentioned before in one whole thing. So this is delta prover, but then there's also Hilbert prover, which does the exact same thing of sub-goal decomposition and environment interactions. Also in the space of coding for scientific discovery, DeepMind made a nice release called AlphaEvolve. So here the idea is you have to code something where you can get a score function in the end, and the better your code, like your code is judged by the score function at the end. And this is pure inference again, there's no training. And the system maintains a database of interesting programs, samples from that database, and improves those further until a very nice program will emerge at the end. And similarly in proving, there's a system called Seed Prover, which will maintain a large database of small facts or lemmas that have already been derived. And it will put those lemmas into the context for the next round. And so the model will gradually prove more and more interesting lemmas until it manages to prove the actual goal. And so what I would like to stress is like these systems that people are building, they use like language models as a kind of building block, and then there's lots of stuff around like this, similar to what Timothy is thinking about when he says, what is a motivated proof? How can we come up with stable algorithms that allow us to turn non-smart intuition into a broader algorithm that manages to solve more complicated problems, but just by repeatedly applying simple rules to the same system. And of course, this is all in its very infancy, but already you see like the overlaps. For instance, thinking about a nice statement that you could try to focus on first, and proving it, trying to really make sure that you proved it until you're happy, then going back to the conjecturing phase and trying to climb up the ladder one step and coming up with an even better conjecture. These sorts of systems are the systems that people are building now, and they're increasingly close to what we think about when you do cognitive science of mathematics, or like trying to understand how mathematics works for humans. And so these were these kind of workflow-like systems, and then I also managed the AlphaEvolve one, where there's a database of programs, and you try to improve the programs that you sample from the database, make them even better, and put the best ones back into the database. Or the same with knowledge, so you could say there's a database of lemmas proved in the context of this proof, and you sample a bunch of lemmas, and then you try to derive further facts from that, and then you send those back to the database here. And so what I would like to stress that like these systems where like the global state is maintained in such a database, or where the global state is maintained in this, the current position of the loop and what you derived over the course of this loop, such systems are very close to this third layer that I mentioned in context learning and ad hoc reasoning. And so, like, people, like, essentially what we don't have in language models right now is episodic memory, or like the working memory is only like constant across one interaction. But by going to text, by going to tokens and storing that text and putting it back into the context of the next model and like merging those contexts and trying to filter what's relevant and so on, people are building systems that are increasingly close to something that behaves like it had episodic memory and was like very careful about what to put into its memory or not. So while prompt engineering was always a bit of like a red herring, context engineering is actually what humans perform as well if they decide to take a new paper and start from scratch on the proof, or try to take one old paper because they thought that was good, or try to take that book because they thought this would really be the best thing to have on the table by doing math. So context engineering really seems to be like the thing that starts working now, up to the point that people say reinforcement learning is dead. We now should do like prompt evolution in this sense. And so the vision that I would like to share with you in the end, before coming to the questions, is what happens if we did the same thing like we did for all the other stages, incorporating the last stage into the training stage of the next iteration of machine learning. What happened if we found a reinforcement learning scheme for structured inference? So that whatever like system you describe, prover, verifier, conjecture, or planner, you can perform reinforcement learning on top of that, and you can create agents just like the ones that people are using nowadays, but specifically trained for it, and so way more stable and way more performant than the vanilla ones that we have right now. And so you can see this work that we're conducting right now on reinforcement learning for structured hierarchical proving as like a baby step toward that vision. And yeah, if I want to give like a bit like more flesh to this idea, I would say in such a hierarchical proof, you have to answer a few questions. So you come up with your decomposition, you decompose into lemmas, you do different independent attempts of proofs for each lemma, and then you receive rewards on each of these. And then you have the decision that you have to do as a reinforcement learner is first, you have to come up with a reward to assign to an action, and you also have to come up with a baseline of how good you think the situation was to begin with. And so, like, if you think about this situation carefully, it's pretty clear, it's very well constrained of what you need to put into each of these. So at the so-called maximum nodes, where any of the attempts has to pass, you would put as the baseline something like the average success rate, and you would put as the reward of the whole node something between the average and the maximum, depending on how optimistic or realistic you are, depending on whether you want to optimize for the average case or whether you want to optimize the whole M attempt system. And then if you're at the minimum node, so here you have to satisfy all lemmas at once, you can put something like the product of the empirical pass rates of each of these. And so I've explained to you, like at maximum nodes and minimum nodes, how to propagate rewards up this tree. But then also there can be something like merge nodes. So you have a partial solution here, you have a partial solution here. Then you put both of these into context, and then you ask the model to generate something new based on both of these. And you will get something, and then you have to ask yourself, like, what was the contribution of each of these, and how do I propagate the rewards back up? So this here, of course, is way more difficult because you don't know exactly what happened at this merge stage. But information retrieval is exactly the field of machine learning that is tasked with this. And in information retrieval, there can be notions like information gain. So how much did Xi help me in producing Y? And you can give a number to that, and then you might be able to use those numbers. And you just use the notions of information retrieval for the merge nodes. Then just briefly, like there can be two other versions. Like there can be something like you have a very same solution that you want to revise and revise until it works. And here you can do skip ahead learning, so you can try to predict the final state, the final action that the model would have taken without taking all the steps in between. Because this is to ensure that the model doesn't always start with mistakes because it knows how to fix them, but it should try to start with as few mistakes as possible by training on the fewest mistakes solution available. And lastly, there can be also cases where it's not about proving, so like something like lean doesn't give us a reward, but for instance, refereeing or reviewing. So such a judge LLM, it doesn't have a ground truth that we can reward it with. But another mechanism that is slightly weaker than reinforcement learning is called the sharpening mechanism. And that just means training the language model on the average outcome of a very large number of calls to the language model. So we can ask for M independent judgments, and then we can train the model to be self-consistent with itself. And this also has been shown to improve performance, even if it's just bootstraps from computation from the same model itself. But so, like to sum up, what I want to stress is people in machine learning, they've been studying different parts of these pipelines, like sharpening mechanisms, information retrieval, value-based reinforcement learning, or like hypertree proof search in the case of these minimum and maximum nodes. But these are examples of like more general patterns that we can use in order to combine different ways of doing inference with language models into large real-world systems. And yet, they're algebraic enough in the sense that like we should be able to derive from these combinators and the propagation rules that I mentioned, the exact propagation rules for the whole system. So the training algorithm that comes with such a graph that someone writes down. And so if you have a system like that, then we can think that as reinforcement learning for structured inference that we are just now seeing in its infancy can become a reality in the years to come. And for me, that is quite an exciting idea to work on in the future, and I wanted to share this today with you. So to sum up, I think formal mathematics and language modeling is just a great match because one of them leads to precision and the other one leads to large-scale exploration and intuition. I think there's a strong trend towards like even larger and more autonomous systems, so less human in the loop, more have 1,000 agents work by themselves and report to you once per day what they're up to. And we as a machine learning community should aim for specific training regimes that make such systems that have way less human oversight even more stable and even more performant. And that's why I think that reinforcement learning for structured inference might be a good approach. And that's what we're seeing right now when we deal with lean proving, but it's a principle that might apply more generally. Thank you so much.